This is problem 6-150. It's on page 326. The kitchen, bath, and other ventilation fans in a house should be used sparingly, since these fans can discharge a house full of warmed or cooled air in just 1 hour. Consider a 200 meter square house whose ceiling height is 2.8 meters. The house is heated by a 96% efficient gas heater and is maintained at 22 degrees Celsius, 92 kilopascals. If the unit cost of natural gas is $1.20 per therm, determine the cost of energy vented out by the fans in 1 hour. Assume the average outdoor temperature during the heating season is 5 degrees Celsius. So he's also got a conversion factor there for us to go from therms to kilojoules. But let's just sketch the system. And I need to double check and make sure that all the numbers are the same. The solution I made is for an older version of the text. Let's see. I'll just hold the book with me, I guess, and make sure as I work it. 200 square meters. Let's see. So the area on the base, excuse me, floor area, 200 square meters. The height of the home H is 2.8 meters, and let's see, the pressure is, trying to make sure this is the same, 92 kilopascals. The temperature is 22 degrees Celsius, and let's see, looks like everything else is the same. Outdoor temperature, 5 degrees Celsius. And the house is maintained at 22 degrees Celsius. There it is. Okay? So let's figure out how much it costs to leave a vent fan on for an hour. Now, one of the things that we have to note is that it says the fan can discharge a house full of air in 1 hour. So that 1 hour that the fan is on, all the air in the house is going to be exchanged. In other words, say it's wintertime, we're going to pull in the cold 5-degree air in the wintertime, have to heat up all the mass of that air to 22 degrees Celsius. So anyway, we'll go ahead and calculate a heat transfer rate, Q dot. And I'm using little q dot because I'm talking about the specific heat transfer rate. So this would be the heat capacity times the change in temperature divided by time. What is this? Well, notice heat capacity that I've written here is just the specific heat capacity. And I'm doing this a little differently than I normally do so I can show you this symbol, this little q dot. This is the per unit mass energy required to change that mass by 1 degree, that one mass by 1 degree, in our case Celsius, because we're in a metric system. Okay, of course, we've got to change it by the difference between 22 and 5 degrees Celsius. We've got to do that in the 1 hour. That's the time frame. Now, I could have just canceled out the 1 hour, but I thought I'd show you this symbol, this rate symbol. Anyway, so the the heat capacity of air at constant pressure is 1.005 kilojoules per kilogram per Kelvin. The change in temperature is 22 degrees less 5 degrees Celsius, and the amount of time is 1 hour. Okay, so little q dot comes out to about 17.085 kilojoules per kilogram per hour. Okay, so that's the rate at which we would have to supply energy back into the home per unit mass. By the way, how much mass is there? Well, there's PV over RT, amount of mass, so 92 kilopascals multiplied by a volume of 200 square meters times 2.8 meters of height, divided by the gas constant for air, 0.287 kilojoules per kilogram per Kelvin, multiplied by the temperature. Now, we have to be careful here. Are we going to use 5 degrees Celsius or 22? Well, the house is maintained at 22, even as the air is being exhausted out and new air comes in. If the house remains at 22 degrees Celsius, then the mass in the house is based on that 22 degrees Celsius temperature. So plus 273 Kelvin. Okay, so a kilopascal times a cubic meter is a kilojoule, and we'll get kilograms from this. This comes out to 608.51 kilograms worth of mass. And so the total heat transfer rate, capital Q dot, let me erase this is little Q dot, the heat transfer rate into this home and out, because the temperatures are remaining constant, is the amount of mass times the heat transfer rate per unit mass. Okay, so just multiplying these two together, you can see how the kilograms will go away. We'll get kilojoules per hour. So when I did that, I came up with 10,396.5 kilojoules per hour as the flow rate of required heating, okay, essentially. So now what about the cost of this? Well, the cost of the natural gas is $1.20 per therm. So let's go work on that a little bit first of all. I don't like therms, I'd rather have kilojoules, so $1.20 per therm multiplied by 1 therm, let's try RM, per 105,500 kilojoules will give me the cost per kilojoules. That comes out to 1.1374 times 10 to the negative fifth dollars per kilojoule. Okay. So there's the cost of energy. So another way of looking at this, I'm just going to drop this hour. Basically, for that 1 hour, if we only leave it on for 1 hour, then we need to buy 10,396.5 kilojoules worth of energy to go back into the home. Okay. Now we have to be careful because we don't buy this much. This is how much heat we need in the home. We have to buy more than that because when we buy the gas in the chemical form, we get energy in the chemical form, only 96% of that energy makes it into the home as thermal energy. And we're told that the heater is 96% efficient. So we actually have to buy more than this. So I'll just go ahead and cut to the chase and calculate the cost of this heat. It would be the cost 1.1374 times 10 to the negative fifth dollars per kilojoule divided by 96%. Well, let's put that over here. That'll make more sense. So times 10,396.5 kilojoules, but we have to buy more than that many kilojoules. So if I divide by the 0.96% efficiency, I will convert these units of heat into units of chemical energy, which will then cancel with these kilojoules. Because this is how much it costs to buy the chemical energy, this is how much thermal energy is needed, and this really is a conversion factor that converts kilojoules of chemical energy to kilojoules of thermal energy. Okay, so really what happens is these cross off with these. Those don't really cross off with each other. Anyway, slight units point. Anyway, this cost comes out to $0.12, costs 12 cents. So if you're the bathroom Nazi and you're always going around shutting off the exhaust fans, just remember for a whole hour it's only 12 cents. You don't have to run to the bathroom and shut it off. It's not that much money actually. And this is you probably don't have a good feel for meters, but this is an average size home. This is not small, not large. And of course this is on the assumption that the house fan only exhausts the entire volume of the house in 1 hour.